The Big Bang from Black Holes. This paper proposes a reframing, not a replacement. It does not reject modern cosmology, override observational evidence, or deny the success of the standard Big Bang model. Instead, it offers a complementary, geometric interpretation that preserves everything the Big Bang already explains, while addressing a long-standing conceptual discomfort: why expansion appears as a beginning rather than as a continuation. The core claim is that the Big Bang can be interpreted as the interior geometric consequence of black hole collapse in apparent spacetime, where extreme compression on one side of a geometric interface corresponds to expansion on the other. What looks like an origin may instead be a transition viewed from a different orientation. In general relativity, collapse and expansion are not opposites in a moral or narrative sense. They are geometric behaviors defined by curvature and causal orientation. Compression occurs when future-directed paths converge. Expansion occurs when future-directed paths diverge. These descriptions are relative to the geometry in which they are embedded. If spacetime undergoes a rupture or inversion when curvature exceeds its capacity, then what appears externally as terminal collapse need not appear internally as termination at all. The same geometric process can manifest as collapse in one causal frame and expansion in another without contradiction. From this perspective, the Big Bang does not need to be treated as an absolute beginning of spacetime, only as the earliest accessible surface in our region's causal history. Inside the new spacetime region, opened by extreme curvature, geometry reorganizes such that all future-directed paths diverge. To internal observers, this divergence is indistinguishable from expansion from an initial high-density state. The hot, dense early universe described by standard cosmology remains intact. What changes is the interpretation of why that state exists at all. This symmetry between collapse and expansion is already implicit in the mathematics of relativity. The equations governing space-time evolution are time reversal symmetric in form. They do not encode a preferred narrative of birth versus death. What gives collapse and expansion their emotional asymmetry is observer position. From the outside of a black hole, collapse appears terminal. From the inside of a new region, divergence appears primordial. The geometry itself does not privilege either description. Crucially, this interpretation preserves curvature accounting. Nothing is created from nothing. Extreme curvature on one side corresponds to redistributed curvature on the other. The initial conditions of the expanding region are inherited, not conjured. This avoids the philosophical tension of absolute origin without requiring cyclic universes, repeating bounces, or eternal recurrence. It also avoids claiming that our universe must spawn another or be spawned repeatedly. The claim is singular and minimal. One collapse may correspond to one expansion, and that correspondence is geometric, not mechanistic. Early universe observations remain fully valid under this view. The cosmic microwave background, nucleosynthesis, large-scale structure, and expansion history are all properties of the interior spacetime region. They do not encode information about what lies beyond the causal interface, nor do they need to. Interpreting the Big Bang as a geometric consequence of collapse elsewhere does not change what those observations measure. It changes only how the earliest boundary condition is understood. The data still describe an early hot, dense, expanding state. This framework simply refrains from calling that state an absolute beginning. Importantly, this is not a claim of proof. It is a consistency argument. General relativity allows horizons, orientation changes, and breakdowns of classical description without asserting annihilation. As emphasized by thinkers such as Albert Einstein and later by Roger Penrose, singular behavior marks the limits of a model, not necessarily the limits of reality. Interpreting those limits as geometric transitions rather than endpoints is a conservative extension, not a speculative leap. This paper exists to allow a sentence that is usually radioactive to be said carefully. The Big Bang may be the interior of a black hole. without implying rejection of cosmology, denial of evidence, or replacement of established theory. It is not a claim about what must be true. It is a demonstration that such a statement can be made in a way that respects modern physics, rather than fighting it. Under this view, the Big Bang is not downgraded. It is contextualized. Expansion remains real. Early conditions remain extreme. Observations remain decisive. What changes is the metaphysical framing. The universe may not begin because time suddenly starts, but because geometry elsewhere becomes too curved to continue in the same way. Collapse on one side, expansion on the other. One process, two perspectives. This reframing is supported not by speculative add-ons, but by structural features already present in general relativity and standard cosmology. The key point is that nothing in modern physics requires the Big Bang to represent an absolute beginning of spacetime. What it requires is an early, hot, dense, expanding state with specific geometric and thermodynamic properties. Those requirements are fully preserved under an interpretation where that state is the interior geometric continuation of collapse elsewhere. General relativity treats collapse and expansion as geometric behaviors governed by the same equations. The Einstein field equations are locally time reversal symmetric. They do not encode a preferred direction labeled creation or termination. Whether a region is described as collapsing or expanding depends on how geodesics are oriented relative to observers. This symmetry was explicit in the original formulation by Albert Einstein and remains a core feature of the theory. From a purely geometric standpoint, a space-time region in which all future-directed paths diverge is no more fundamental than one in which they converge. Both are allowed solutions. Singularity theorems strengthen this support by clarifying what they do and do not claim. The theorems associated with Roger Penrose and others show that under certain conditions, classical space-time descriptions become geodesically incomplete. They do not claim that space-time begins or ends in a physical sense. They identify the breakdown of the classical manifold description. This leaves open the possibility that continuation requires a different geometric region rather than further extension of the same one. Interpreting the Big Bang as such a continuation is consistent with what the theorems actually establish. Cosmological horizons already demonstrate that beginnings and endings can be observer-dependent without contradiction. In standard Big Bang cosmology, the particle horizon defines the earliest time from which signals can reach us. This is a boundary of access, not a boundary of existence. Interpreting the Big Bang as a horizon-like interface aligns with this logic. What we call the beginning is the earliest surface of causal contact in our space-time region, not necessarily the beginning of all geometry. The symmetry between collapse and expansion is also supported by how space-time behaves near horizons. As discussed earlier, horizons represent orientation changes in causal structure rather than physical walls. Inside a black hole, all future-directed paths point inward relative to the external universe. In an expanding universe, all future-directed paths diverge outward relative to earlier times. These two behaviors are geometric inverses. Treating them as connected through an extreme curvature transition preserves causal consistency without requiring new physics. Importantly, this interpretation does not alter any early universe predictions. The cosmic microwave background, primordial nuclear synthesis, large-scale structure, and expansion history depend on the interior space-time geometry after the Big Bang surface. They are insensitive to what, if anything, lies beyond that surface. Standard cosmology already treats the Big Bang as a boundary condition rather than a dynamical event explained by known physics. Reinterpreting that boundary condition as inherited from collapse elsewhere does not contradict observations, because observations do not probe beyond it. The conservation of curvature and causal accounting further supports this view. General relativity does not allow curvature to appear without cause within the equations. It must be sourced or inherited through boundary conditions. Treating the Big Bang's extreme curvature as inherited rather than spontaneous avoids introducing an unexplained origin while remaining agnostic about what lies beyond. This is a conservative interpretive move, not a radical one. Finally, the motivation behind quantum gravity research itself provides indirect support. Much of that effort is driven by the recognition that classical space-time descriptions fail at extreme curvature, not because reality must end, but because geometry must reorganize. Even without adopting any specific quantum framework, the expectation of reconfiguration rather than annihilation is already built into the field's trajectory. Taken together, time reversal symmetry, singularity theorems, horizon behavior, observational insensitivity to pre-Big Bang conditions, and the acknowledged limits of classical geometry all support a careful conclusion. Interpreting the Big Bang as the interior geometric consequence of black hole collapse elsewhere does not rewrite cosmology. It respects everything modern cosmology measures while offering a structurally consistent way to think about why expansion begins at all. It replaces an absolute origin with a geometric transition without claiming more than the science allows.